where the whole electromagnetic spectrum comes from. Because if you look at a metal or any element, actually, it doesn't have to be a metal, and you guys saw that she had those tubes, or she had the different colors that she showed you. What happens with the different elements, you've got the nucleus that's still positive, and then you've got the energy levels that around it where the electrons move that are very random, and that's very important here. These are random energy levels, and they are different for every single element. They're not fixed. So what happens is you've got this, you learned in grade 8 or somewhere, that you've got these electrons moving in these energy levels. And then what happens is that these electrons jump up. I don't even think I sent this video to you. I just did the photoelectric effect once, but I will share it. What happens is that these electrons somehow gain energy, and they have to gain energy through something. So you must either heat them, so you guys put them in a flame, so you gave them thermal energy. You can also give them electric energy, which in a fluorescent light that you see on the roofs, those lights that are normally in kitchens, you those fluorescent lights also they give them electrical energy, or you can give them light energy. And that is where what comes into this section. So if a certain light comes onto this, or heat, or any kind of energy gets into this electron, the electron can only live in this energy level. Remember, they are discrete energy levels. They can only live there if they have a specific amount of energy. So if they have too much, they're going to leave, and they're going to try to get to the next energy level. Now, what's very important, and this is where the whole quantum physics thing comes in, if this gap here is exactly 200 joules, that means that electron can only go there if it gets exactly 200 joules. If it gets more than 200 joules, it will leave the atom and it will become an ion, because then it's going to be a positive ion. So that's how ions form. But if it doesn't get it, if it gets exactly 200, it will go up to that energy level, and now it's there. And that's what we call the excited state. It's there in a higher energy level, that is the excited state, and it doesn't want to be there, because remember, everything in nature wants to be as lazy as possible. So it would love to come back. So this is the part that they've taken out of your syllabus for some reason. So this is the absorption spectrum. So the electron have to absorb energy to get to that higher energy level. Now, where the IEB starts is they're already in that energy level. They already absorb the energy somehow through light or heat or electricity, and they're now already in that excited state. What is nice, if when we did used to do this, it's actually, I'm just going to quickly tell you because it sometimes helps to understand it better. So if you have a gas here, so if you have, and you send the whole Rooikabov, the red, orange, yellow, green, blue, you send all the colors come in. So you send white light. So I'm just going to not do all of them, but you're sending white light into this gas, for instance. So if this was a gas, so if you have a gas tube and you have white light here, and now you have all those little atoms here. So there's your nucleus, and you have all those little atoms there. I'm going to make up values again. But let's say the light goes through, and the electrons of this specific element, if they're sitting there, they need exactly, say red light has 350 joules of energy, which is not true, but if it does, then it will, that 350 joules of energy will be absorbed, and that electron will move to the higher energy level. So if you're sitting here with your eye, very creepy big eye, looking on this side, then you are not going to see the red. So what you're going to see is you're going to see all the colors. You're going to see the orange coming through, and you're going to see the green coming through, and the blue, and all of it. But the red will be missing, and where the red was supposed to be, there will just be a black line. So I'll show you just now, it shows quite nicely in the notes. So this would mean that the red light was absorbed. So that's why this is called the absorption spectrum. It absorbed red. But now, what we are looking at in the IEB is if you now take the source away. So you're taking this away, and we look at the gas, all those electrons are already sitting there in a higher energy level. And this is what you guys did. You looked at the substance when these electrons were already excited. So let's say it absorbed red and it absorbed blue. So what you guys saw through that little thing that they made you look through is everything is black, and then all of a sudden there's a red line, and then it's black again, and then all of a sudden there's whatever it absorbed, it's now going to give off. So now the electrons fall back because they don't want to be there. It's too much energy for them. They fall back, and now they send out again that red color, and this blue one falls back, and it now sends out that blue color, and the rest of it will just be black lines. And this now, because they are emitting these different colors, this is now called the emission spectrum because it's emitting those colors. And this is what you guys saw. You saw black, 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 and then color line, black, black, color, color, color. And this is different for every single element because every element has different energy levels. So that means it's specific to an element. And this is how they often ask us in an exam, how do scientists use this? Because it's a little point in the SAGs. How do scientists use this? And it is in the notes, but you'll see that they can identify different elements according to their spectrum. So if you have a substance that you don't know, we know what the spectrum looks like for hydrogen or for helium or for carbon or for anything. Then they can match it and see, okay, it's carbon. And this is also by the light that's coming from stars, they can actually see what the stars are made of, what elements they can find in stars. So yeah, I think it's pretty exciting. I like this. So that's the emission spectrum. But now where the calculations comes in is we are only going to look at them falling down. So now if they fall down that energy level there, they're going to send out a light with specific amount of energy. And remember, we can calculate that energy as it says here by again saying HF. If we have the frequency if we have the energy gap, so if we know it's 200, we can say 200 is equal to HF, and we know what H is, so we can work out the frequency. So we can work out exactly what specific electromagnetic wave is coming from this element. And if they ask you for the wavelength again, we just change that equation into hc over lambda because we know what h is and we know what c is, and we can work out the wavelength if we know that energy gap there is 200. So they often, now when they give it to you in the exam, they're not going to draw the circles. They're going to show it to you like this. So when they mark it, they can sometimes call it E1, E2. They sometimes call it N1, N2. That just means, so E1 would be this first energy level in which the electrons move. And E2 would be that second energy level in which the electrons move. And so on. And these gaps, again, for every element is going to be different. And that's why we get different colors from different elements. So these show it nicely. So these are going to be then emission spectrum. So we don't look at the absorption spectrum. Again, so if you look at hydrogen, this would be hydrogen always. So whenever there is hydrogen in a substance, you will see these lines, or if it's pure hydrogen, you will see these specific lines. And sometimes we have gas tubes filled with these gases, and you look at it, and that's exactly what you see. And then helium would be that. And in the stars, there's a lot of this, and that's why these two are common. Please look at just for what we did last time. If you look at the wavelengths, remember it says here wavelengths is nanometers. Now, for the whole electromagnetic spectrum, you're normally going to get wavelengths that are pretty small, except if it's radio waves. Radio waves are huge wavelengths, and then this means if the remember, if the wavelength is very small, we know that the frequency is very high. Just keep that in the back of your head as well. And then you'll see in the notes, it does tell us that they each have their distinctive spectrum, so we can, if there's a mixture, so if you take those tubes that they let you look through and you look at it, you look at for instance, the projector, you'll see a bunch of different colors because it's different lights, different gases that are there. We did put the absorption in the notes just so that you can see, so that's also emission. So absorption would just be exactly the opposite. So if this is the mercury emission spectrum, so this is what came out of Mercury, then if you go and you look at the mercury absorption spectrum, and this is not Mercury, doesn't matter, then the absorption spectrum would be all the colors, but the ones that are absorbed, you can see those are the black lights, like I said earlier. They're not there, you don't see them, but to see this you have to have a source. So that's why this little thing here is quite cute to see, because you're going to have a source that creates the light, then it creates the continuous spectrum. So this is like the sun. So if this was the sun, you would see the continuous spectrum, which is all of it. If you let the white light shine through a gas, then it will absorb certain colors and you will see those certain colors. But if you don't have the source and you just look at the gas after it's being excited, then you'll just see the emission spectrum. So those are the three spectrums that are possible, but for the IEB, we focus on the emission spectrum. Does that make sense? I know I've been talking a lot constantly, but yeah, I like this section. Is that, you understand this? Okay. All right, so let's look at the way they're going to ask it. So these, in the notes, there are a few examples that we can go through. So yeah, so that's the whole photoelectric effect. Remember, it's normally about 20 marks in your paper, but don't leave them out. It's still 10%. So if you get stuck on other questions along the way, go do the photoelectric effect question first, because it will boost your confidence because it's really easy, and it's 20 marks in the bag. It's normally between 15 and 20 marks in an exam. Often they don't have photoelectric effect in the multiple choice, because if they waste 2 marks there, it only gives them about 15, 13 marks to ask later in the paper. But sometimes there are multiple choices. So let's just look at this one. This one was quite tricky. This was labeled a higher order one, because it says it's got the 3 energy levels, X, Y, and Z, and then the energy levels, so they tell you, let me just do it properly. So when you get a diagram, remember to write things on the diagram that you read. So it says X, Y, and Z are energy levels in an atom. So these would be energy level number 1, for instance, or 2, doesn't matter. Energy level 2, energy level 3. So this is part of your bigger atom where the nucleus is here somewhere. But they'll never draw it like that. They'll just show you the levels. And then it says the difference between energy level X and Y. So X and Y. No, I lie. The difference between X and Z is twice. So X and Z is twice the energy between X and Y. So this gap here, this one here. So if this is X, this is going to be 2X. But that's energy. Now you need to go think about all your direct proportions. So they say if the wavelength of a photon emitted as a result of P is lambda, what is the wavelength of a photon emitted from X to Z? So from X to Z. So we know that if this falls happen, yeah, so they say P, I'm just checking that I've got the right labels of P, so that's going to be lambda, and they're asking you for this one. We don't know what this lambda is. Okay, so you're going to use your normal direct proportion. But what is now, remember they're giving you the energy. So they say the energy of P, if the energy of P is X, then the energy of Q, that jump there, this Q, is going to be 2X. Now, what is the energy directly proportional to? Yeah, remember our equation. So we know E equals HF, and we can immediately jump to the other equation as well and say E equals HC over lambda. Now remember all these proportionality questions, you can do that. You can see, okay, what are they asking me? And you change the equation in the form of that. They're asking us for lambda. So they're saying, what is lambda? So we can say lambda is HC over energy. Because this time they didn't give us the frequency, so we'll rather work with this equation. So this is the case, it's lambda when it is Q. Oh, talking nonsense, B. So this is lambda. Now you do it the same as all those other proportionality ones. The quickest, easiest way is still to say there's an equal sign, so whatever I do on the left-hand side, I must do on the right-hand side. So H is a constant, so it stays the same. C is a constant, so it stays the same. What is changing about when we now go to Q? What is changing? Energy becomes 2E. And that's all I'm changing. So the only thing I'm doing is I'm adding a 2 here at the bottom of the line here. So now, why does it feel as if it's too easy? So it should be that the wavelength is going to be twice. I just want to see if it's 3 times. X, twice the energy difference. P is X, wavelength X to Z. Yeah, no. Sometimes they make it for an between one. So this one wasn't all that hard because now whatever you add on the left hand side, you add on the right hand side, and you can see that the answer is just going to be lambda over 2. Happy? Okay. So these questions, I think I sent you the version with the answers already. I only realized that later. Did you see? So you have the answers, but you could still try and do them. So we can look at some of these questions because it is a mixture, and then we can look at the past paper question. Is that fine? Okay. They do like putting it in an electric circuit because they're testing concepts here. So what you need to realize is that when we are emitting all the different things that are, again, directly proportional, when we're sending electrons out, as soon as they're connecting it to a circuit, you need to remember that electrons is charge. And the way charge is linked to current, charge is Q. So the way charge is linked to current is that current is equal to Q over T. You get it as Q equals IT on your information sheet, I think. But the current is Q over T. So if you have more charge sent out, then the current is going to go up. If you're doing it slower or faster, if the time goes up, so if the time goes up, it means it's going slower. So when the time goes up, the current is going to go down. So just remember this when they're asking you about current in a circuit, current produced, because this is basically how solar panels work. Because what happens is during the day, you're sending the UV light onto your solar panel. It's sending electrons out because of the photoelectric effect, and those electrons are then being stored on a capacitor, and you can use them then later when there's no sun. So it's quite clever. So now so this is one of the applications of the photoelectric effect. You can see here comes the UV light, and the cathode is there. So the cathode is and the anode is there, you can see positive, and they have to do it that way around so that the anode that is positive, can attract the electrons that are being emitted, and as soon as there are electrons being emitted, you will see a current. If there's no electrons being emitted, you will not see a current. And we need to go through the steps for you to answer those questions as well, so that you don't mix up things. Okay, so the first question says UV light. Okay, so they're giving you 100 nanometer. Immediately remember to change that into 100 times 10 to the minus 9 meters. And then they say if you interrupt the beam, the drop in current activates the alarm. Okay, so this is how those sensor beam alarms work. Now, threshold frequency. Can you remember what the threshold frequency is? Remember, that's the minimum frequency that the electron needs to be emitted. So the electrons are sitting here and they need work function. So then what they need is the work function. So the work function belongs to the electrons. The electrons needs at least the work function energy to be emitted. That means the light must come in with a frequency that is high enough to make the energy equal to the work function. So this will be the energy of the photon. This will be the threshold frequency. So then this energy becomes the work function. Okay, so those ones there. So threshold frequency is the minimum frequency that the light needs. Please always link frequency to light, because it's the minimum frequency that the light needs for it to emit an electron. So that's threshold frequency, and they're going to ask you one of those, either the work function or the threshold frequency. They will ask you. Okay, so now it says how will the increase, and this is where this is the only place where it becomes a little bit tricky. They say how would the intensity of the UV light influence the ammeter reading? Now we already know there is an ammeter reading, so we know electrons are being emitted. So the UV light did have a frequency higher than the threshold frequency. So your first mark would be that UV emits electrons. We know that because the question basically told us that. But just make sure that we know that it emits electrons. But now if we increase the intensity, what are we actually increasing? It is the brightness, yes. So intensity is brightness, so that means there's more light coming at your eye in a second, yeah. So kind of the power as well. So that means we are increasing, and this is the one thing they're going to look at, the number of photons. So intensity, yes, is an increasing in the brightness, definitely. But both of these will increase the number of photons. So those packets of energy hitting the cathode. And that's what they're going to look for. They would want to see that you know that an intensity doesn't change energy. The energy remains constant. Okay, so they wouldn't probably give you a mark for that yet, but it's very important that when you increase the intensity, the energy remains constant because it's still UV. It hasn't changed color. For the energy to change, the color must change, or the type of electromagnetic wave must change. But here it stays exactly the same. So it's the number of photons that is hitting here that is increasing. And if you're increasing the number of photons, you are increasing the number of electrons that are being sent out. And now remember that equation. You can even quote the equation. You know that current is equal to Q over T. So if we have more electrons being emitted, then the current will go up. So they're saying explain So how will the increase in intensity influence the current? Therefore, the current will increase. Okay, so they love asking these questions, either decrease or increase. Just remember that if this was, for instance, red light, and the red line did not emit electrons, then would the intensity do anything? No, because it doesn't have enough energy to start off with, so no electrons are going to be emitted. So even if you send 1,000,000 of them per second, it's not going to change. Each of them have to have enough energy to emit that electron. And then obviously they have to have a calculation question. It's always there. Um, Actually, it wasn't, I think last year there wasn't a calculation. It was quite weird. That they tell you that the work function of the metal is that. So when you read the question, because the terms can get a bit confusing here, I would say just immediately write down what you read. So they're telling you that the work function of the metal is 8,7 times 10 to the minus 19 joules. The energy is always going to have a big negative power tennis. Tiny joules is a tiny unit. Just remember, if they give it to you in electron volt, you need to always convert it into joules. We want joules for our calculation. They say calculate the maximum velocity. So they're asking us for the velocity of the electrons. Which equation links the velocity of the electrons to the energy? So if I want the energy of the electrons, what equation will I use? Can you remember? It's the EK equation. Oh. So it's just going to be EK equals half mv squared. So as soon as you see they're asking you for the electrons, you know you're going to use EK is equal to half mv squared from your equation. So that's what they're asking us, and they've given us the wavelength of the light. So they've given us the light wavelength, which is 100 times 10 to the minus 9 meters. Now when you've written it down like that, if you go to your information sheet, you will see there is only one equation with EK in it. So it's going to lead you to that, but they didn't ask you straight for EK, so you needed to make this link. The other way of choosing the correct equation is to remember that when there's a mixture, there needs to be a plus in the equation, because I cannot add apples and bananas, so that means I've got energy of electrons and I've got energy of light. And the only equation that has that is that one that says E equals work function plus EK. And so this one is the one that we're always going to use, but you need to remember that this first energy is the light. That gets converted into the work function of the electron and the kinetic energy of the electron. Don't confuse them. So this light one, we need to think, did they give me the energy of the light, or do I need to change this to give me something that they did give me? So they did not give you the energy of the light. So what are you going to change this E into? Did they give us the frequency? You could use HF, but then you need to go and work out F first. Perfect. Because they gave us lambda, don't put in an extra calculation because it's going to be a waste of time. And if you make a mistake, it doesn't carry over. So be careful. So just use HC over lambda because they gave us that. They gave us the work function. So that one we're going to leave as it is. They do not ask us if they asked you for the energy, kinetic energy of the electron, then you would leave it as EK. But they don't ask us for EK. So this part, like we already said there, we're going to change the EK part of our equation. we're going to change into half mv squared. And again, that was your hardest job, to get the right equation so that we now can fill in our values into that equation. So now we have the constants. We have h. I don't remember it now. It's 3, I don't know. You have it on your information sheet. You have an information sheet with you. I'll quickly get it for us. I'll just put like I had last week, I'll just put all the values there for us. Yeah, because this is the one with the lots of equations and lots of constants, because yeah, almost all the constants here in your information sheet is for this section. It's actually insane. But yeah, just copying it for us quick. Yeah, sorry, the units in this one that I've just opened is a bit weird, but that's not really going to affect our lives now. So there are the constants. I'm just going to, while I've got it open, I'm just going to get the equations for us as well. You can get used to seeing them where they are on the information sheet. You need to always just study with it next to you. That you can get used to finding them. Alright, so you can see where we started there was getting this equation from the information sheet. The reason why they say max is because of electrons they are a little bit, it's a bit of a random emission. And that's why some of them will not always have the maximum kinetic energy. But if that energy level is that exact energy, then they will have the maximum kinetic energy. So don't worry too much about the word max. It doesn't change our lives. And then here, you can see that here also the kinetic energy is half mv squared, and it's max. But even in the question, you will see that they said calculate the maximum velocity. So for these calculations, we're always going to deal with the maximum velocity. Okay, so now we've got HC. Let's see if we can get an answer for this. This one is, in this section, your calculator skills gets tested to the limit because there's a lot of powers of 10 that you need to include here. So H, now we can see it here on our information sheet. There it is there. So it's 6,6 times 10 to the minus 34. C is the speed of light, which is just 3 times 10 to the 8. Lambda, they gave us in the question, is 100 times by 10 to the minus 9. Now, it's insane important that you put the brackets here, because if you don't put the brackets, I don't know, always something goes wrong. Then the work function again is given to us as 8,7 times 10 to the minus 19 plus, you'll see, it's a lot of powers of 10. The mass, what mass are we going to use here? That's important. So where would you can see, there it is on the information sheet as well. So that's 1,6 times 10 to the minus 31, huge power of 10. And then I ran out of space here, but then v squared. So now the rest is all our calculator's job. And you can solve for x, but you're going to see that if you do it that way, maybe we can have a race. You can do solve for x, and I'll do it the old-fashioned way. Do you use solve for x for these ones? Okay, yeah, so don't worry then. But just please type it in for me, because I want to see that you doing this correctly on your calculator. I'm also doing it quick. Are you done? Okay. I stopped hearing noises, so I thought you were done. Yeah, your calculator does most of the job for this question. Answer. And then please put your answer here in scientific notation. Because, yeah, I know people write all kinds, so put three significant figures. Yeah, I'm going to write my answer down, and then we can see if you get the same. What I got. I might be wrong. I'm hoping I'm right. I did try and type properly. No, that's one of the reasons I wanted you to type it in. So, if you get an answer on your calculator, you need to think about, is that answer realistic or not, especially in this section. Because if you get a speed of you got something times 10 to the 31, is that what you said? This is way faster than the speed of light. Remember, the speed of light is given to you on your information sheet. So you must always use it as a guide. The speed of light is 3 times 10 to the 8. So this is like 4 times the speed of light, and nothing can move that fast, not even an electron. So speed of light at the moment is the fastest speed that we know that anything can move at. So that will tell you that somewhere on your calculator you made a mistake. Where if you look at the answer I got here as the 3,72 times 10 to the 6, remember it's still just meters per second because it's still just a speed. But that's a little bit more realistic because if the speed of light is 10 to the 8, electrons move pretty fast as well. So you will always get it around the speed of light or a little bit slower, but you'll never get it bigger than the speed of light, and you'll never get a negative power of 10. So this power of 10 that you got should point in to tell you somewhere in your calculator you made a mistake. And that's why I say just please make sure you put in all the brackets. So what I did is I typed in I always start on the opposite side. So I typed in this whole thing and got an answer for that. Then, because there's a plus there, did you remember to minus this or did you divide by it? That's one of the most common mistakes people make. Because there's a plus sign here. Remember, once you've got this answer, you have to minus this whole thing. And if you divided it, that would make sense that your answer has now got a big positive power of 10. So you divide by that, then I times by 2, and then I divided by this whole 1.6 times 10 to the minus 31, and then I got the square root. So it is quite a job. So if you do want to write one more step in between, you can, but it is a bit of a waste of time. So just go, and if your answer is in the range of the speed of light, leave it. You can always come back later and check the calculation. But this is one place in your exam paper that I would definitely say check your calculation skills, your calculator skills. Always go and do it again and make sure you've done it correctly. But if you get in the range of power of about from 10 to the 5 to 10 to the even 10 to the 8, because sometimes they can move closer to the speed of light, but it will not be bigger than the speed of light. So you just made a mistake on your calculator. I'm sure if you type it again, you'll get it right. But does the method make sense? Okay. So just be very careful here with your calculator. You can go and do it later and see if you get that answer. Let's look at the next question, which I think was also a multiple choice. Yeah. Oh, these ones again. I did send you a little video with the graphs because they do let you get confused between these graphs. And you need to, when you read the question, you need to think, is it electron? Is it light? Or is it a mixture? Because so many people focus on this graph that 90% of the country chooses that graph because they don't even read the question. They look, oh, I've seen this graph before, let me just choose it. And it's not always the right answer. It's only the right answer when you've got electrons and light mixed. So let's read the question. The question says, which one of the graphs best represents the relationships between the energy? Now, also, this was a bit sneaky because they called the energy of the photon W, where we are used to it being the work function of the electron. So they called the energy of the photon W. So actually, that means that W is now becoming HF for this equation because they told us that E is equal to W. So it's not the work function. The W here is not the work function of a photon and the frequency of the radiation. So it's exactly that equation that I just wrote down that they wanted you to look at. So if you look at that equation and you have W and F, from this equation, what relationship is there between W and F? Yeah, so the answer was just B. And 90% of people chose C because they're so used to seeing this graph. So please be careful. This graph you will only have if they're talking about electrons as well. So it's electrons and light, where the others are. Sorry, I'm just doing my phone on silent. Okay, so that's the only time when it's not going to cut through the origin. So just be careful there. So this is a typical graph that I've just said. They ask, and this was the graphing question I think last year, May or somewhere. So if we look at this graph, now you can see the maximum energy of the photoelectron. So these are the electrons. And this is the frequency of the incident radiation. So this is the wave. So now we know it's that equation that we're going to use that says E of the wave is equal to work function plus EK. And then just remember to get it in the shape here, you need to put the EK in the Y position. So we're going to put EK in the Y position equals, that will give us then, if we swapped it around, E wave minus the work function. I'm just putting that step in. But then because they're giving us the frequency, we're going to change this into HF minus the work function. So this is actually the equation that they are using for this graph. Don't memorize it. Remember that it comes from there. Because otherwise sometimes, people memorize things and then they answer the question wrong. So now you can see that EK is on the Y. So this is Y equals mx plus c. So now if you go and look at what you've done, EK is on the y-axis. We're happy with that part. F is on the x-axis. So we're happy with that part. Then we can see from here that the gradient is going to be Planck's constant, and we can see that, what color has I not used? And we can see that minus the work function is equal to, remember the minus there, is equal to the y-intercept. And you can see it's going to be negative, the y-intercept. So it all makes sense. So then they say, use data from the graph to determine Planck's constant. So if you know all of this, what is Planck's constant going to be? How are we going to get Planck's constant? Oh, please be careful. You can, it's there, but they say use the data from the graph to calculate Planck's constant. So can you just go and get it from the information sheet? No, but when you do get it, you can go and check that it is actually close to what we have on our information sheet. So we can do that after we've gotten the value for it. But because they say calculate Planck's constant, you can't. You have to use the graph like we just said. So what of the graph is equal to Planck's constant? Gradient. So please write that down because that's your first, they look out for the fact that you actually use the data from the graph. If you just go and write the value down, you're going to get no marks for this one. So you have to say there that your gradient is equal to Planck's constant. And you know that your gradient is then going to be change in y over change in x. And now you can find any two nice points on this graph. Yo, they didn't really make life easy for us, did they? Oh, that one isn't too bad. Let me just make it a little bit bigger that we can see a bit nicer. Because remember, when you go and choose values for the gradient, always go and choose values that are nice points. So let's just see here. That one, I don't know, kind of looks as if it's crossing on the two dark lines. So I think it could be a safe one to use. So that point there. And then remember, show them that you make it easy for them to give you marks. Show them that you have used the graph. So draw a little dotted line to your x and your y axis. And I would really even write there, because you are busy with question A, I would write there and say this is question A, or 1 or 2, whatever it is. So that's our first point that I would say we're going to use. So that's going to give us 15 minus something over 30 minus something. And then, but just be careful. On this graph, actually, I could have done it without it, and you'll see that you are going to get really weird values. So you need to know that the top, the y values, you need to multiply it by 10 to the minus 19. And the bottom values, you need to multiply it by 10 to the 14. Please always look, especially for this section, look out for the powers of 10. So we can use that, and then we can find another nice point. But if we are going to use this intercept, then we have it for future use as well. So we can use this point, which looks like, is it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yeah. So it's 7.5. Do you also see 7.5 there? I think it's about 7.5. And then our x value would be 0. So I would actually put in the coordinates there as well, 30. Because if you put the coordinates in, they don't actually, they don't just look at that. So we're going to say 15 minus 0 on our, oh, I did this the wrong way around. Sorry. X first, remember, so it's going to be 7, 5, and then 0. Okay, so there we go. So on our y, it's going to be 0, and on our x, it's going to be 7, 5. But now these are the values straight from the graph, and that is not what we have actually. So you need to remember on the y, once you've typed that into your calculator on the top of the line, to say times 10 to the minus 19. And at the bottom of the line, we're going to say times 10 to the 14. Remember, I did say frequencies are always going to have a big, big power of 10. And energies are always going to have a small power of 10. So it's a way of making sure that you've got the right value. So let's type this in and see if we actually get Planck's constant. I'm just typing it in quickly. And now, so now you can check. Again, if you type this in wrong in your calculator, you're going to get a very weird answer. Why am I getting a negative answer? This is so weird. You cannot get a negative answer, so I did something wrong this time. Let's see if we get the same. Okay, now it looks better. They actually made this too perfect. Because if they make it too perfect, you can just go now and go and write down the value from the information sheet. But normally they say use 2 decimal places. So then at least write your answer as 2 decimal places. So I got almost 6, 7. You get that? What's happening with that calculator? Okay, perfect. Okay, now remember, still it's an answer, so we need a unit. So now Planck's constant, how are you going to know what the unit is for Planck's constant? You can use the units on the graph. So you can say it's y over x. So it could be joules over hertz. That would be a safe way. An even safer way is to go to your information sheet. Remember, you have your unit for Planck's constant on your information sheet, but it's the same thing. So joules over hertz, remember hertz is seconds to the -1. If the seconds goes to the top, it will just be joule times by seconds, which is the value that's given on your information sheet. But joules over hertz would be absolutely fine. But because it's something that is on your information sheet with a unit, the units you could go and get from the information sheet. Okay, so for this, please remember if they say use your graph, use your graph. Don't go and just read off the value from your information sheet because they'll definitely penalize you for that. I can't remember if we even gave 1 mark for doing that. I don't think so. I'm just going to make it smaller again. Alright, so then they want to know. Determine the minimum energy required to remove an electron from the target metal. What are they asking for? Minimum energy required to remove an electron. Nice. So when you know your definitions very well, then you know that's what they're asking for because that is basically the definition that they're giving you there is the minimum energy required to remove an electron from the metal. So they're asking us for the work function. Now on our information sheet, we have, I've killed the information. Let's just go and get it. From our information sheet, we have an equation for work function. So you just go to your information sheet, find the equation, and you're going to write work function equals H times F naught. Okay, now work function is what they want. H we know is 6,6. So you could use now your value or you can use the information sheet. They didn't say hence. If they said hence, then you would have to use your value, the 6,67 times 10 to the minus 34. But in this case, they would have had to mark both right. And F naught, now where are we going to get, what is F naught? Remember, if this is the minimum energy, then this one would be the minimum frequency. And what do we call that minimum frequency? Perfect. So that's the threshold frequency that goes with the work function. But now we need to get that threshold frequency. Remember, it's the minimum frequency that will emit an electron. Now, if you're looking at your graph, here all these electrons here have a speed, but only here was the first electron emitted. So only at this frequency here was the first electron emitted. So when it cuts your x-axis, and this is the frequency on your x-axis, the place where it cuts the x-axis is always going to give you your threshold frequency. So you'll get used to spotting it from these graphs, but always make sense out of it first as well. So here, no electron, no electron, no electron. That's why they didn't have kinetic energy, because there were no electrons emitted. But as soon as I pass that 7,5 point, then electrons were emitted. So this threshold frequency is that value that we read off there. So the threshold frequency will always, if it's this graph, will always be your x-intercept there. So now we can put that into our equation, and we just please again remember, look out for powers of 10, not just in this section, but especially in this section. So 7,5, or that's what we read it off as, times 10 to the 14. Now let's see what we get our power of 10 for our work function now. So just type that in again. Just check that you get the same answer. What was your power of 10? Did you get 5 as well? Okay, 19. And what would the unit be? Yes, because when we calculate, we use joules, not electron volts. So it's going to be in joules. And now if you think back to the other questions that we had before, yeah, can you see that work function was 8,7 times 10 to the minus 19. And so for all the energies that you've seen were about in that region. And it's also in the region of an electron volt, which is 1.6 times 10 to the minus 19 as well. So for the energies, you're always going to get energies in the region of minus 19. So if you get a power of 10 that is like that, then you know you're probably right, and you don't have to go and recalculate it. But if you get a positive power of 10 for your joules, then you must know, calculate a mistake. Or you get a very, very like 40 power of 10, then you again know, calculate a mistake, because it's the big thing that happens here. Okay. And then this last question is just basically theory. It says, explain how the photoelectric effect, it's those points that I pointed out here in the notes, explain how the photoelectric effect produces evidence which illustrates the particle nature of light. Remember, they thought that an electron would just be sitting there, gathering light, gathering energy, and then eventually it will be emitted. Doesn't matter what color. But then they realized it's not going to ever happen, and they need to, so you're going to have to say it is, so you need to talk about the energies. Some energy light will never, I can't even spell energy, some light or some waves will never emit electrons. even at high intensity or long time. So that's the one thing. And then you need to say there's no time delay. So when electrons are emitted, there is no time delay. So therefore it's a particle interaction. And then the last one that they were looking for there is that more photons, which means intensity or brightness if you want, same thing. So if there's more photons, which means more intensity or brightness, then more electrons emitted. So those would be the three things that they're looking for. That even if you pump up the intensity, nothing will happen. Particle interaction, more particles, more kicked out. So it's a kind of a collision thing. Okay, so that they do often ask this in weird and wonderful ways, that question. That's why you just need to know those points. They sometimes ask you what were expected and what did they see and what did they not see. And then you just need to make sure that you can answer that. This is O. I do want to, which one do I want to throw out? Um, yeah, don't worry about, let's do it. I always say don't worry about it, and then I'm so scared that she's going to throw something into the exam like it. But I want to change these values in this question because it was from the previous examiner still, not the lady that's setting the paper now. But they're saying electron A is at the lowest energy level. So that's that one closest to the nucleus. Oh, I didn't actually speak about this. And this has come up twice in an exam. These values are negative. And that's kind of weird. But it is because when you are looking at those energy levels, when they are far, far away. So this question is actually a nice one to show it. When it's far, far away, it's almost like when you know that potential energy, we just did it, so it's fresh in your mind. EP is mgh. So you know that so let's say this is the Earth, and if that's your height, if your height increases, your potential energy increases. So if you're in the next energy level, your height increases again, so your energy increases. So that means the further it is from that nucleus, the higher the energy must be. Now, if you are looking at these values, if they were positive, it would mean the further you are from the nucleus, the smallest your energy will be, and that's wrong. So when you move further from the nucleus, the energy must increase. But if you are far, far away, so if you're on Mars, you have zero potential energy with reference to the Earth because the Earth has no effect on you anymore. So that means the values increase and the maximum value that it ever can be is zero. So if values increase to a maximum of zero, it means all the values must be negative for them to increase to zero. And also, you need to add energy, or when an electron falls down, it's losing energy. So that means it must have less energy. Again, if you're going down and these values were positive, it would mean that they now have more energy. So just remember that the values increase to a maximum of zero, and the further away you are from the nucleus, the more energy you must have. And therefore, these values must be negative so that they could increase the further you're going from the nucleus. So you will always see negative values, but remember, energy is still a scalar. So you don't stress too much about it. So if they ask you for a wave that is emitted, we can just use this for a bit of explanation. So let's say an electron is there and it drops down to that energy level. You know that when it drops down, it's going to send out an electromagnetic wave. And that electromagnetic wave's energy is going to be equal to HF. Now, if I want to work out that energy, I just look at the difference. So don't stress about the negatives. You just look at the difference between 15 and 8. The difference is 7. So this is going to be 7 electron volts is going to be equal to HF. Just remember, we can't work in electron volts. And often in these energy levels, because it gives us such nice round values, they do give you electron volts. But you need to remember them to say 7 times by 1,6 times 10 to the minus 19, because that gives us joules. And then because H, you saw on that information sheet, H is joules seconds. So therefore we have to convert to joules, and then you can work out your frequency if they ask it. So don't stress about the negatives. It's just a difference. But the reason why it is because the energy must increase as we go further from the nucleus. So if we look at these values, they ask us in which of these do you say ionization, excitation, or nothing will happen. Now we already said this gap here is exactly 7 electron volts. So if it absorbs a photon with 7 electron volts, then it could go exactly up to that energy level. So it will just end up being an excited electron. If it gets 4, can it go anywhere? No, so nothing will happen here. So anything less than 7, so even this one, if it gets anything less than 7, nothing can happen. And if we look at this big gap here, the difference there is 15 electron volts. So if it gets more than 15, then it will leave. It will totally leave. So the only one that gives us that is C. And that would mean it becomes an ion. So the electron leaves and it becomes a positive ion, like I said there in the beginning. So this will give us ionization. And then the 11,5, we need to find an energy level that is exactly that. So is there any energy level that has exactly a gap of 11,5? They are all whole numbers. So just by checking that they're all whole numbers, we already know that there's no gap that's going to give me exactly 11,5. So remember, it has to be exact because of the whole quantum thing. The whole quantum, can't spell quantum, the whole quantum theory is that it has to have the exact, the energy must be the exact amount. So actually there, that was the only tricky one. Also nothing would happen because it doesn't give us the exact number. And if it's not the exact number, it's not going to happen. It can't go live in here in between energy levels. It has to be, it's either in or it's out. Let's remember that. Okay, let's look at the next one. Okay, so this one is now a nice one. They say it drops from an excited state of 1,5, so it was here at minus 1,5, and it drops down to minus 13,6, emitting a photon. Now remember, a photon is just a wave that you are sending out. So when that electron falls down, it's going to send out a wave, and that wave will either be E equals hc over lambda, or it's going to be equal to hf, depending on what the question asks you. So you can already think through it. And then they ask you in the first one, how much energy is released from this transition? So you can just say 13. You don't even have to show the calculation, because then some people get the negatives mixed up. You're just looking at the difference. So you can really just always go biggest minus smallest. So it's just going to be the 13,6 minus the 1,5, which should be, oh, I don't even get the right answer here. Is it 12? No, 8. No, 12,1. Do you get that? Okay, so that's 12,1 electron volts. Now remember, we don't work in that, but because the question said in electron volts, don't stress about changing it yet. Then they want to know, where does this energy go? And we already said it is sent out as an electromagnetic wave. And then they want to know, so it goes basically to the photon. And then find the frequency of the photon emitted. So how am I going to do that? Which one? Right. So just E equals HF, and we have the energy because we've just worked it out, which is 12,1. But can I use it like that? So I'm going to times it by, where am I going to get that value that I need to times it by? Okay, so always go and look for it. It is there. It's just, and it even tells you that it is an electron volt. So please go and just find it there. You'll see the last one there is the electron volt. So don't trust your memory in an exam. It's exam stress. So go and copy it from there. 1,6 times 10 to the minus 19. So that's our energy. Our H is given to us is 6,6 times 10 to the minus 34, if I remember correctly, and F is what they want. So now we can just stick that in our calculators. Again, I want us to actually do it so that we can check those powers of 10. Because for frequency, what power of 10 must you expect? Must it be a low power of 10, a high power of 10? Let's see what our answer is, and then we'll talk about it again. Minus 34. That's what I got. Is that what you're getting? Okay, so can you see it's a very big power of 10. And remember when we had the diagram, the electromagnetic waves are so close together, so they always have a very high frequency, very low wavelength. And we're going to do that now in the next one as well. What is the unit for frequency? Yeah, just don't forget to put a unit. It's hertz. Remember, hertz is also the same as seconds to the minus 1, if they ask you that in a multiple choice. And in the next question, they ask us to work out the lambda. So now we can work with E equals hc over lambda. Or, remember, if we have the frequency, we actually have the wavelength as well. But then you're carrying over, if you made a mistake here, you carrying over that area into this one. So I would rather go and do this whole thing again and say 6,6 times 10 to the minus 34 again, and that gives us 8 times 10 to the 3 times 10 to the 8, sorry. Now we stop there. 3 times 10 to the 8. See why there, read it off your information sheet that you don't do what I just did. And then our lambda is given to us, we don't have, but our energy is given to us as the 12,1 times 1,5. comma 6 times 10 to the minus 19. Such long numbers here. And then we're going to get lambda. So let's see what the power of 10 is going to be there. I should have kept that value in mind. I've got it still. See what we're getting. I might have made a mistake on my calculator. My calculator's not liking me right now. Okay, let me just do it properly. Okay, divide by. Well, my answer looks way too big. I get a positive power of 10. Let me just. Okay, so what did you get? Did you get an answer? No, it takes longer just typing. I can see what I did wrong the first time. Gives me an error again. I don't know what I'm doing. Okay, that sounds better. So this is in meters. So now remember, if you think back to values that we got for lambda before, it was like nanometers, which is minus 9. So that makes, so if you get an answer like this, I would say it's probably right, because for your lambdas, for the electromagnetic waves, you're always going to get a negative power of 10. Where for your frequencies, you're always going to get a positive power of 10. If these are swapped around, you must know that you've done something wrong, because the only lambda that's going to give you a big value, like in meters, but not even times 10 to the something, it could be like maybe 10 meters or so. That would be a radio wave, which they don't ask about often. But the electromagnetic spectrum, the Roy-Gaboff, the red, orange, yellow, green, blue, you will always get a negative power of 10 between like minus 7 and minus 9. And for your frequencies, you'll always get a huge power of 10, which is like the 15, 14 times 10 to the 14. So again, here you must be very aware of the ranges in which your powers of 10 must be, so that you know that you've made a calculator error, because they creep in so quickly. Then the number 6 there is the question that I spoke about earlier. They do ask that sometimes. Explain how they use the emission spectrum, and that is they can identify different elements because they can look at their emission spectrum and then identify them according to a known spectrum that we have available, or they can see what different elements stars are created from by looking at the spectra that reaches the Earth. Okay, so you can just make sure that you know at least 1 or 2 uses of the emission spectrum for the exam. They ask it every now and then. It is in the notes. Just don't say that it's a fingerprint for an element, because people love saying that. Yes, humans can be identified by a fingerprint. An emission spectrum does not have a fingerprint. So yes, it's like a fingerprint, but you cannot use that as house scientists. They marked it wrong. So please don't say it's a fingerprint. It's not a fingerprint. It's a way of identifying different elements, because different elements will have specific emission spectrums. Like a human has a specific fingerprint, but it isn't a fingerprint. So be careful there. It's even in some textbooks, I know they say that. This one we can kind of leave because it's the same as the previous one, so you can go and do that one because it says neon light drops from there to there, and they want the wavelength. So again, you're just going to look at the difference, and that will give you the energy in electron volts, and then you're going to, again, the same as what we just did, you're going to use E equals hc over lambda because they're asking us for the wavelength. We're using that equation. The energy there, the difference, is going to be your E, and you plug and play and you get your answer. Okay, same calculation as which we just did. I'd rather look at the next question. So it's this graph again, EK max. Remember, EK max is the electron. It's only the electron that moves with kinetic energy. And this is the wave. So again, it's that equation that has the mixture. What value do we get here where it cuts the x-axis? Perfect. So this would be the threshold frequency for the sodium. This is the minimum frequency that you need from the light to emit a sodium electron, and this is the minimum frequency that you need from the light to emit a silver electron. And now you can see for sodium and silver it's different. You need more energy for silver than what you do for sodium. So if you look, the first one is again just the definition, but then they say which metal, sodium or silver, has the largest work function. So which one has the largest work function? Silver, because the work function is directly proportional to the threshold frequency, because we have the equation that work function is equal to h f naught, and h is a constant. So because h is a constant, we can say that work function is directly proportional to the threshold frequency, and therefore it will have the higher work function. If they ask you if this was 4 marks, then remember, if you're looking at the nucleus for sodium, that electron for sodium is about there. So sodium has, if you're thinking about the nucleus, I think it's 11 protons pulling it in, where silver has way more protons pulling that electron into the nucleus. So it needs more energy for that electron to be emitted. There's different things that could play a role. It could be the distance from the nucleus or the strength of the nucleus. So you just look at the actual one that is the highest and then explain it according to which one is the highest. Then they say name the physical constant, remember, represented by the slopes. In this case, what would the slopes be? If you think back to this, I'm just going to go back to that one. Because this, oh no, did I not leave it? I didn't. Oh, it's fine, I can do it again because it's important. I didn't leave that equation for us. It's very, very important that you can manipulate this equation, because remember the equation that's on your information sheet just says E equals W naught plus EK, which in a way means kind of nothing. Here we've got EK on the y-axis, so we always have to rewrite the equation into this form, E, and then on your information sheet I would go and write here E photon, so that you know it's the wave. And this again then becomes E photon minus the work function. So if you're looking at this equation again, the frequency this is the photon. So we're going to change this into HF minus the work function, and this is going to be half mv squared, or just EK if we just worried, and that because they've given you EK. And again, this then gives us Y equals mx plus c. Super, super important, because now you can see from our graph EK is on the y-axis. I'm just doing it fast again. Oops. Yeah, I can do that. Frequency is on the x-axis. Very important. And then I can see that my gradient, my work function is the negative of the y-intercept, and my gradient is going to be h. So if this question is saying what physical constant represents the slopes, what are you going to say? Perfect. And please don't just say h, because they said name the physical constant. So if they say name the physical constant, write out the name. If you want to put h in brackets, you can, but don't just call it h. Now that last question they also like. They say if light of the same frequency is shone on each of the metals, in which metal will the injected photoelectrons have a larger maximum kinetic energy? Which one will have more energy once the electrons leave? Because they do use light of the same frequency. Okay, so let's think about that one. If you look at the threshold frequency, the threshold frequency gives you the work function, and remember this work function is the energy that the electron absorbs. Um, so the electron takes this energy. So for which of the two metals will the electron take the most energy? Silver. So silver electrons are going to take the most energy. So if the silver takes the most energy, remember the kinetic energy is the energy that's left over after the electron took energy to escape. So if silver takes more energy to get out, it's going to have less energy to leave with, where the sodium takes less energy to escape. So that means that it's going to, because they said light of the same frequency. So the light that comes in, like that first diagram that I drew for you last time, the light that comes in, let's say it's got 100 joules of energy. And the sodium takes, I'm just going to use these numbers we have, takes 5,9, and the silver takes 11,2. Which one is going to have the most energy, kinetic energy to move away with? The sodium. So that's, please think about these ones. The common answer there was silver, but they didn't ask you to explain. It just said which one, so it would be a 1 or a 2 mark question. I think it would be a 2 mark question because there's a lot of thinking involved in it. But if they said explain, then please remember the one with the lower work function will absorb less energy, which means more kinetic energy is available. And the one with the highest work function will absorb more energy, which means that, I don't know if I said less or more. If it absorbs more, less is available for it to leave with.